Yes, this time, let's talk about free lists, allocators, in other words, variable size allocators. In the case of the fixed size locator we talked about earlier, we cut the memory pool into a fixed size when we were assigned an activity. But on the contrary, this time, in this case, it is called a variable size allocator, which has the advantage that the same memory pool can be allocated to multiple sizes in the way we want, rather than a fixed size. So basically, let's see how this allocator works. This is where the concept of header comes in. So every time we allocate data, this header gets allocated with it. In other words, we're always going to allocate this form of header in front of it and data in back to this memory ripple. So this header basically has two things. One is about this down jacket and the other is the size of this data. It contains content about. So what exactly is this down jacket? Now, for example, the arm is usually called an alignment. What this means is that I'm going to allocate data, but I'm going to allocate it in multiples of this arm. So what arm? Or what 24, what 32 or 64 in memory like this? This means that the starting address will match the multiple of the arm. So, for example, so far we're trying to allocate some data to the memory pool. However, I saw that this allocation is only like this, up to the memory address, whose last size was 20 previously allocated. Now, so when we allocate here, for example, 10 bytes, let's assume you're assigning some data. So you don't put a header right in front of this. How to do it is, give me padding so we can match it in multiples of this arm. So we're going to add this data, and then we're going to do this by placing the headers over here. So this is the concept of this padding. So why on earth is this down jacket going in when I say it's for some kind of optimization? Now, what do you mean? In the case of a 64-bit computer, to the CPU allocates memory in PAL bytes. It means ordering data. The CPU reads and processes it. What do you mean we have 20? If the CPU wants to read triple data, 2888 reads and processes the data one by one like this. Now, but what kind of data does this size have? Let's assume the CPU is trying to withdraw. The CPU always fetches data in this alliance unit, but now it's like this, and the start memory start address. Let's assume that the memory start address is 086. At this time, the CPU brings one lump like this. But, for example, what kind of data does this place have? Let's assume that it's allocated over this span. Now, this clothing position data is actually smaller than this PAL byte. So, for example, it was arranged like this. Then you can process it just by reading one data. But if it is allocated across two blocks like this, even if you try to read and process the same O byte size unit, you get two memory reads. So, in order to prevent these things, they gave me down jackets, not here, but here, so they matched it like this. To do this, this padding exists. So that's basically the concept of this header. So we basically do this. How is the initialization done? First, give me the allocation size with this parameter and then give me this alliance size. How do I align the alliance in bytes? Well, will you match the PAL byte or give me something like this? So this variable size locator writes a list of connections internally. So we create some kind of node and manage the data in the form of a connected list. So what information do these nodes contain? Let me just say that when we enlist such a variable large locator, we repeat the release of allocation. Now this red is the assigned kit, and the rest of these are the ones we can use. This can happen. So each of these is how this information is managed in the form of a linked list. So we're going to use this internally connected list. So first let's say this variable size allocate size is cloth. So we're going to assign some node that has information about the size of 2000. It's not that the size of your node is 2000. I can now be assigned 2000. The size is 1000. And then I will create a node that says the starting address is a liquid type. Now, in this case, let's see what happens when we do the actual assignment. Now, basically, we're always doing padding calculations. Every time we assign the allocator, here at the beginning, a node called 2000 is already in the connection list. Then, if we think about the first allocation case, we allocate data with a size of 20. When you said, look at 2000 and allocate this 20 with 1000 is enough. So let's take a 20 plus header size from this column and say, what is the remaining size except for the data I actually need to allocate this 20? Then I have removed 2000 nodes from this existing connection list, and now I can allocate 230. I added the size to the connection list, and then this is essentially assigning the data and then handing the data over. Now let's look at a case where we repeated the deallocation from this locator several times. Then, as we saw earlier, if we repeatedly release the allocation like this, there will be spaces of various sizes. Yes? So when we are like this part will be like this. So we want to set up 50 data. But this memory space is 100. So this one is 20 and this one is 10. Well, I'll try 300 like this. What's important here is that you have to check each of these 4 nodes to see if there's a child that I can actually assign 50. So you keep looking from the front. So there are 102, so I allocate it. So I split it up and set it to allocate 50, and now only this place will be left as free space. As I've shown here, I need to find a child that I can assign among the various nodes in the memory ripple on this current connected list. Because of this, we usually have these disadvantages. It takes time outside the afternoon for the purpose of time. Now, let's take a look at the case of freeing memory. So, what do we do, for example? Let me try 50. if you hand over some data rather than 50, we said earlier that we would put a header in front of this data together. When you go to this data, you get information about how many fights it is. So I'll try 50. Now, as I said, there are a lot of links. So now, well, for example, there will be connection lists with the start address stored together, like Young X, Sam Young, or 8 Young. For example, if this header is Young X or 7 Young, it is now my allocatable space, because I ordered free now. So, after creating a new node, we put it in a space where it can fit and add it to the connection list like this. So this is how the action happens, and the important thing here is that we go through this merging process. For example, I connected it and put it in the middle of the stang, like this, but when I found out this guy and his memory are connected in series, this means that you can combine these lists into one, not two. Yes, so you can say that this merger process is rough, which is a characteristic of this dissolution process. So to sort it out, as I showed you earlier, this is a bit of a complicated logic. Well, there is the concept of a header, there is the concept of a padding, and there is the concept of a connected list. And the advantage instead of a self is that we have a variable size. You could say flexible. You can put in different sizes, but some drawback is that this exploration time process takes n hours in the afternoon. I know that this drawback exists in that when we want to make allocations, I have to look at each node to see where the actual allocatable space is. And then there's a way that you can do a little bit more optimization within this structure, and that's with this release allocator, the light size, the allocator. Next, I would like to inform you that there is a way to combine and utilize fully balanced binary thread black trade, or ABLT.